Hello everyone, my name is Marlon Morales, and today I am pleased to present our research entitled Impact of Surface Uniformity on Luminance Measurements for Energy-Efficient Lighting Design. Thank you all for being here. In this presentation, I will introduce the motivation behind our work, describe the methodology we used, discuss the main results, and conclude with the key findings and future perspectives. Let's begin. Lighting obtained from natural or artificial light sources has a critical role in most activities performed by humans. Its efficient use focuses on several metrics, with luminance being one of the most important for characterizing lighting systems. Thus, this magnitude is used for research related to standard regulations perceptions such as brightness, glare, and uniformity. Due to the broad fields of applications of luminance, it is necessary to know the accuracy of the measurements being carried out with this magnitude, with the luminance meter being the equipment used for this purpose. These devices are increasingly used in the evaluation of lighting levels, and the results are employed in various fields of the study, ranging from natural lighting, as well as comfort, energy efficiency, and other more varied fields, including health. Studies related to vision also use luminance meters to characterize performance parameters related to size and of contrast of objects. Considering that its application extends to so many fields, it's essential to note the technical merits of the equipment being used, in general to ensure that the measurements taken with an instrument are reliable and traceable to international standards. Is necessary to perform its calibration. According to the beam, is the process of comparing the measurement instrument with a known reference standard to determine its accuracy and, if necessary, adjust its operation. Currently, methods that employ CCD or CMOS cameras are more prevalent in industrial and scientific fields due to the shorter time it takes to measure luminance. The pixels that make up an image are assigned luminance values through software, generally in grayscale. To calibrate these devices, techniques such as grading boards are used, allowing for multiple exposures and the assignment of a defined luminance value. In the work developed in, the calibration is performed similarly, but also employs a colorimeter. Another way is to process this image based on readings obtained from a digital camera and contrast them with a spot luminance meter. This contrast is performed over a physical element that, according to the studies, is usually a neutral gray. Calibration surface like the X-Rite color checker classic target or to find reference luminance value defined as the spot luminance meter. As in the case of, furthermore, measurements taken with CCD or CMOS cameras exhibit an effect known as vignetting, which refers to having darker areas in the periphery of an image due to the optical path used. To characterize this effect, it is necessary to ensure the uniformity of a luminous surface that will be used to calibrate the cameras. As stated in, there is difficulty in obtaining a surface with high uniformity that covers the entire camera sensor, and an alternative method is employed but requires much more time for calibration. According to the presented works, it can be observed that the elements against which the contrast is carried out to calibrate the cameras are physical and therefore do not obtain a constant uniformity across their surface. Despite advances in luminance measurements with CCD or CMOS cameras, these devices are contrasted with a traditional luminance method through a spot luminance measurement. On the other hand, a measurement must be accompanied by some quantitative indication of the quality of the result. Its measurement uncertainty, several methodologies can be employed to meet this requirement, with JGCM 100 being one of the most well received by the community due to the endorsement from CIPM from this procedure. As stated, a viable option for the calibration of both cameras and luminance meters is to assume that the lack of luminance uniformity of the illuminated surface and incorporate it as a source of uncertainty in the measurements. This paper presents a methodology for that. Mathematically, the amount of light reflected from a surface and perceived by the observer is known as luminance, and is established through the equation 1. Additionally, luminance can also be defined as we can see it in the equation 2. If it can be ensured that the luminance remains constant within the surface elements, equations 1 and 2 can be combined is given by the equation 3, where d is the distance between the source and the detector ensuring correct alignment. It can be considered that the angle between the source tends to 0, as well as that the distance is considerably greater. With this, we get the equation 4. The equation 4 is used in practice for the calibration of luminance meters, considering the surface is uniformly illuminated. In this way, the most commonly used procedures for luminance calibration focus on direct comparison, which involves contrasting a reference device against a luminance meter under calibration. In this process, a luminous surface is measured, which could be the aperture of an integrating sphere. The difference in readings between the equipment under calibration and the reference equipment is then used to determine its error or correction. This research established the influence on calibration uncertainty introduced by the lack of complete uniformity of a surface. The methodology can be applied both on a luminous surface or a physical reference element for calibrating cameras. To establish the luminous uniformity, there are recommendations in the lighting normative. It will be used as are the overall uniformity and longitudinal uniformity. Additionally, a third equation is included in the analysis, which is directly related to the coefficient of variation. This is a parameter used in various topics and applicable in this study. Equations 5 and 6 are established in normative, assuming a normal distribution of the measurements, while equation 7 is used in various fields to study, for example, the regularity of a surface. This research conducted analysis assuming a normal distribution as established by the standards. Subsequently, this paper also considers the analysis when this assumption is not met with normal distribution and studies these effects overall uniformity results. For this purpose, non-parametric statistics are used, that is, the median of the measurements, to characterize the measure of central tendency and interquartile range for its dispersion. The estimation of the typical combined uncertainty for the uniformity is obtained from the recommendations of JCGM, where their general form is equation 8. The points measured on the luminous surface are independent of each other. Therefore, they are considered uncorrelated. The experimental scheme consists of a sphere and a luminous meter mounted on an optical table, with a distance of 1.5 meters between them. Several precautions were taken to reduce stray light in the measurements by placing screens. The sphere has an opening, and over it a 21 mm diameter opal glass was placed, resulting in a uniformity illuminated translucent surface. The experimental scheme is shown as in the figure you can see now. A stabilized AC voltage source was used to reduce variations in radiation source. The voltage regulation is 0.2%. The light source was in an incandescent lamp, and therefore taking measurements it was left on for 10 minutes to reach stabilization. With these precautions, it was ensured that the variation in luminous flux emitted by the incandescent lamp would not have a significant impact on the results. The sensor is a LMT Model 1009 luminous meter. It was used with a angular field of 6 minutes and aligned with the emitting surface opal glass. Then we established points identified from A to Y. In turn, 292 luminance values were taken for each of these points. You can see in the picture the distribution of these points. For this purpose, the field of view of the luminance meter must be appropriate to take measurements to each selected point of the opal glass, avoiding overlap to each measurement point. Subsequently, the normality test is conducted to determine the statistic that will be applied in the analysis to the number of luminous measurements per point. Anderson-Darling is used. For each point, the relevant statistical parameters such as mean and standard deviation, or shape and scale factors, depending on the distribution, were extracted. These parameters were then used to perform a Monte Carlo simulation, generating a significantly larger synthetic dataset compared to the original number of measurement repetitions. Due to the optical constraints of the luminous meter, scanning the entire surface of the opal glass is impractical. To extend analysis across a larger area of the luminous region, a new data point is estimated by interpolating between the two nearest measured points, using their respective probability density function. A new vector was then constructed, with its elements ordered as illustrated on the left side of the figure. The generation of these points is done with the purpose of extending the analysis to a larger area of luminous surface, conducting a uniformity analysis using these generated points. Once the luminous value were taken in the indicated quantity and location, their normality was evaluated using Anderson-Darling test. None of these 25 points taken could be considered to follow a normal distribution at the 95% confidence level. Subsequently, the outlier test with Dixon's Q was conducted on each of these points, finding that 5 of the measurement points, D, J, P, R, T, contained one outlier, which were removed to continue with the study. Once the outliers were removed, the Anderson-Darling normality test was conducted again, and the non-normality of the measurements remains, shows the histograms corresponding to values measured at 6 points. A superimposed normal curve is shown in red. It was verified at 95% confidence level that none of the PDFs could be approximated to a normal distribution. The goodness of fit analysis confirmed that none of these measured point groups followed a normal distribution. Based on this analysis, the most suitable PDF was selected for each point, as we can see in this table. Then we can see an example of simulated PDFs for 6 points of the luminous surface. In red, the fitted curve defined in Table 1. To estimate the measurement in sectors of the luminous surface that were not susceptible to measure, new points are generated from PDFs of the measurements. The distribution of the obtained data is shown in this picture. It can be observed that the distributions resemble a normal cube more closely without actually being one. Once the data from generated points is obtained, the measure of central tendency and its perspective dispersion can be determined from each of them. With these luminous values, equations 5, 6, and 7 are applied to find the uniformity of the luminous surface and associate it with an uncertainty. The surface area captured by the luminous matter at 6 minutes field of view is characterized by calculating the projected diameter for each measurement point using the equation 9, where d is the distance between the sensor and the luminous surface, and theta is the angle in radians obtained from the field of view selected in the equipment. Under these conditions, a projected area of 5.4 mm squared is obtained of the luminous surface. Considering the measured and generated points, approximately 75% of the opal glass surface is covered. To the calculation of luminance uniformity, we define 3 scenarios to find the uniformity on the opal glass. At first, it was considered that the measurements follow a normal distribution at each point. The measures of central tendency and dispersion are the mean and the standard deviation respectively. Second, the PDF for each point was worked with established in Table 1. The measure of central tendency will be the median, while the interquartile range will be the dispersion. And the third scenario, the generated midpoints showed that they do not follow a normal distribution. The measures of central tendency and dispersion are calculated using the equations from scenario 2. The uniformity of the opal glass was calculated for each of these 3 scenarios presented in this table. It is necessary to associate the measurement uncertainty for each of them following the provisions in the equation 9. This is also applicable for the estimation for the uncertainty of the standard deviation as well as the uncertainty in the interquartile range. In this table, we can get the relevant equations from these calculations, and the equations are presented for both and include their corresponding sensitivity coefficients. Equation 9 was applied to all mathematical models of uniformity to estimate the combined uncertainty, which represents the dispersion of luminous values that can reasonably be attributed to the non-uniformity of the luminous surface. The uniformity results obtained from different equations, together with their associated combined uncertainties, are presented in the following table. The results show the longitudinal uniformity is the most demanding equation to verify the uniformity of the luminous surface. This equation presents the lowest regularity results. On the other hand, the equation that shows the highest uniformity is the one that considers the coefficient of variation. Regarding the uncertainties, present the highest uncertainty being on the order of 1 times 10 to the minus 3, while in the order of two uniformities the uncertainty estimation is lower, being on the order of 1 times 10 to the minus 6. When calculating U0 and UL, the measured values are very similar, in some cases differing only in the third significant digit. This situation is different when considering generated values. In this context, direct measurements provides a more reliable estimate of surface uniformity, whereas attempting to infer a value from surrounding measurements introduces greater uncertainty and can lead to uniformities far from those obtained through direct measurements. This study quantified the uncertainties associated with the non-uniformity of luminous surface, highlighting its potential to be incorporated as a parameter of calibration of luminous methods or in surface characterization. The results indicate that despite ad precautions implemented in the experimental scheme, a uniformity of approximately 90% was achieved under laboratory conditions. Further studies are recommended to evaluate the impact of surface non-uniformity on luminous measurements in situations where a homogeneous luminous surface cannot be guaranteed, such as luminous assessments on motor vehicle traffic roads. That concludes our presentation. Thank you all for your attention and interest. I hope this presentation has provided a clear overview of the study and its main findings. So, thank you all.